Okay,
All
now
right,
you can
I'm
record.
recording. Yes, you
Okay.
can see the recording.
Okay. So more questions.
On the same page, page 110.
Yeah.
So actually, the author talks about book 4, but they say direct delta, and then function is in the quotation mark.
Yeah, because it's not a function.
Ah, okay. And then
Right. Because if you look at this, if you have a function which is 0 everywhere and something else at 0, the integral has to be 0, right? Because 0 is a set of measure 0.
Yes.
So that integral on the right here does not make sense in our sense of integration.
Oh, okay.
And even if you have a function, if you have f of x, let's not consider it the Dirac delta, but I just define f of x to be infinite if x equals 0 and 0 if x is not equal to 0, then the integral f of x dx over rd is the same as the integral over rd
minus 0.
Minus 0, exactly, f dx, which is 0.
0.
Right?
Right.
So that's why this is not a function. This just this
Ah.
wouldn't work. That's why they're quotation marks.
Ah, I see.
We actually call it. I have to give Dirac his due. I have to capitalize him
The
because
honorable
I actually started studying physics in 1980 with someone who was a student of Dirac's. So I have to give him his due. But in maths, we call it the Dirac measure. Because as a measure, you could understand what it is. You could say that the Dirac measure m of a set E is equal to 0 if 0 is not in E, and 1 if 0 is in E. And that satisfies all the properties of a measure. It's countably additive and all this stuff like this. So let's not call it M because M is the Lebesgue measure. Let's call it a different measure, mu. And as a measure, it makes sense. It also makes sense in a different way as let me erase this stuff here. So if you look at the space of continuous functions on RD, right? So this is a vector space. Has all the properties of an infinite dimensional vector space. And then if you look at a map, let me call it delta. Delta from RD to R, which takes a function f to its value at the origin, that's a linear functional. I mean, it's a linear map in the sense of vector spaces that it preserves addition and multiplication by scalars and all this. And so the delta, if you want to write this as delta of x times f of x dx, that's just because linear maps are often written as integrals on infinitely dimensional spaces. That makes sense.
Mhm.
And it makes also sense in this sense that this is f of x d mu,
Ah, okay.
right?
Mhm.
Where mu is the Dirac measure here.
Uh-huh. I see.
But it's not a function,
Mm.
even though Dirac called it one, but he didn't know what he's talking about as far as
Okay.
functions go.
Sure. So the following question is that they on the page 111,
Yeah.
the top portion, they say the mass of D is concentrated at y is equal to 0.
Mm-hmm.
So what does it mean by mass?
Mass means, it means exactly this sense,
Ah, okay.
that if E contains 0, the measure of E is 1.
Uh-huh.
So all the mass is concentrated at 0.
I see. Okay.
See, if you look at this one, there is what he says as Lebesgue-Stieltjes measures there. If
Mu is increasing?
if G is an increasing function, right? Then you can write down what the Stieltjes integral of f dg is, at least in one dimensions. What did I just do?
Yes.
I just went to a new board. I now found out how to get infinitely many boards. You can write this integral f dg. So this is, it doesn't have to be increasing, but g has to be non-decreasing. And the Stieltjes integral is basically, you know, the soup over all partitions, summation f of, if f is positive,
Xi.
xi, g of
G.
xi plus 1 minus g of xi.
Yes.
Right. That's what the Stieltjes integral is. And now if you take g to be the function which is 0 for x less than 0 and 1 for x greater than or equal to 0, then the integral f dg is just equal to f of 0. You can easily check that by direct computation.
Yes. Okay.
More questions?
The example 1, when there's a phi non-negative bounded function, they say it's a approximation to the identity, and then the simple verification is left to the reader.
That's called exercise 1.
Okay. So I did the sure.
We're gonna go over that
now, later.
Later.
Okay,
Let's
sure.
go first to text. I want to make a remark about example 3 because we have a lot of applied people in here.
The heat kernel.
Yeah. If you look at the heat equation, and I'm just looking at it in one dimension. in t dimensions, it's the same. It's just mass writing down, right? Du dt is equal to d squared u dx squared, and with an initial condition u at 0x is equal to f of x. Then if you consider, if you write down u of t and x is equal to 1 over 4 pi t to the 1/2 times e to the negative
Square?
let me take that back. I have to write that. Times the integral over r e to the negative x minus y squared over 4t times f of y dy. So if you compute du dt, and if you compute d squared u dx squared by differentiating under the integral sign, assuming that we're allowed to do that, then you will see that this function u of t and x actually satisfies this equation. And it's in several dimensions. It looks exactly the same, except that there's an absolute value up here.
Instead of, yeah.
It's instead of just x minus y squared. And moreover, u of t and x, as t goes to 0, goes to f of x.
Just like the identity.
Yeah. I used here that if you take k delta of x minus y times f of x dy is the same as f of x minus y times k delta of y dy. And this is just a change of variables.
Oh, okay.
So are kernels mostly used for physics?
Again?
Are kernels mostly just used for physics?
No, not really. First of all, it's called the heat equation, but it could be also called, it's also sometimes called the diffusion equations. If we look at the coronavirus,
how the coronavirus spread in the medium?
right. So how does heat or diffusion spread? It spreads, you have molecules wiggling and they kick their nearest neighbors, right? And that's this d squared u dx squared is the kicking of the nearest neighbors. And that means if they kick their nearest neighbors, they transfer kinetic energy to their nearest neighbors, and the nearest neighbors start wiggling, right? And that's how the heat is spread. Now, viruses which spread by contact or even through the air, like the coronavirus,
Mm-hmm.
follows essentially the same equation.
Mm.
There's other things too, because you have to make sure that your nearest neighbor is actually susceptible to the virus
Mm.
for it to spread. So that it's a nonlinear equation, but you have this same behavior here, and it's so this equation shows up, or similar equations show up not just in physics, they show up in chemistry, they show up in biology, they show up in social science, as a matter of fact, because some things in social science spread like viruses, like what is it?
Rumors.
What?
Rumors?
Rumors, yeah.
Radical ideology?
Radical ideology, yes. and what I wanted to say is, what's that Canadian boy pop star? What's his name? Yeah, well,
Sorry, no idea.
okay, so, but it doesn't matter. But
I think
zombie
also
infections.
I think
Yep,
it's used also in the financial market too.
Yeah, it's used in the financial market, and in general, what I write you down here is not a good kernel, but it's a prominent kernel. Let's do our one.
Hmm.
F of y dy. So the kernel here is 1 over x minus y, which is certainly not good, right? Because it blows up when y equals x, right?
Mm-hmm.
And it's not integrable.
Mm-hmm.
So it doesn't satisfy any of our good kernel things. But this thing is actually known as what's called the Hilbert transform.
Oh.
That's pretty important in just pure mathematics.
Mm.
And it has to be taken as a grain of salt. But I mean, if you take if you call this, let's say, f star of x now, the Hilbert transform, the transform is actually an isometry from L1 to L1, which is really nice.
Yes.
If you understand how to read that. And that shows up in a lot of places, both in pure mathematics, but also in structural mechanics of cracks. But,
okay. You say cracks?
Cracks, yeah. Like cracks in a bridge.
Next question is on page 113.
Yep.
So they talk about this absolute continuity.
Mm-hmm.
So I'm wondering whether the absolute continuity is the function f itself or the integral of the absolute value of f on set E.
Well, if you look at proposition 112 in
page 65.
Yeah, on page 65, it says there exists a set of finite measure B, a ball, for example, such that the integral over the complement of the ball is less than epsilon. So
I thought it was the second one, no?
and there exists a delta greater 0 such that when this is less than delta, it is the second one.
Mm-hmm.
If you have A of R1 minus A of R2
Oh, okay.
in absolute value, this is the integral y less than R1 f of x minus y minus f of x dy minus same integral of y less than R2
Mm-hmm.
of the same integral.
Mm-hmm.
And this is less than, this is equal to the integral R2 less than y less than R1 over the annulus
Ah, okay.
of this absolute value dy, right?
Mm-hmm.
And this is less than epsilon if the measure of this annulus is less than delta, and the measure of this annulus is less than delta if R1 minus R2 here. R1 minus R2 is less than delta to the 1 over the over whatever the new d,
Mm-hmm.
something like that.
I see.
So
I see.
that gives you directly
Mm,
the continuity.
I see. Whoa. Okay. And then thank you. There's an inequality in the top of the page. A sub r less than equal to 1 over rd.
Yes.
So the derivation of the second inequality, Professor. The L1 norm of f plus Vd of absolute value of f. I guess it's similar to the exercise 1, or?
Yeah. Well, the first one is just you estimate the integral absolute y value y less than or equal to r.
Mm-hmm. You consider the entire space Rd?
By the entire space.
Ah, okay.
And the second one, you remember the integral is with respect to y.
Mm-hmm.
You just pull out the f of x of out of the integral, that you have just what you get is the volume of a ball of radius r around 0, and that is the new d times r to the power d, and that's why you get the new d.
Yes, yes. Okay, thank you. Next question is on the page 114.
Anyone has a question before that?
Oh.
What's page 114 the question?
So it's a 450 question, I guess. So
yeah.
That there's this number n large enough so that is 2 to the negative k, the tail n, is less than epsilon. They say by making delta sufficiently small that we get that first inequality.
Yes.
Please help.
What?
Please help why we get that inequality, Professor.
Well, the A2K,
Uh-huh.
the A2K delta
Mhm.
is I'm thinking I'm losing my stylus here. I am. No charge. Oh yeah, here we go.
Oh.
The A of 2K delta
Mhm.
is the integral absolute value y less than 2K delta
Mhm.
f of x minus y minus f of x dy, f of y, no, minus f of x.
Mhm.
Take it back. Dy,
Mhm.
right?
1 over.
So
There's
you integrate over a ball of radius 2K delta times y.
uh-huh.
And again by 112.
No.
Again by 112. If you make the measure of this ball small enough, you can make that less than any epsilon. In particularly less than epsilon over capital N.
Ah, I see. So that n is just just epsilon over n is a certain number.
Yes. The n is
Okay.
given because we choose n so large that the sum is less than epsilon.
Mhm.
And then so this is prop 112 in chapter 2.
Mhm.
Again. And so then epsilon and n are given. So you just then choose delta small enough such that the measure of this ball is small enough that this is epsilon over n.
I see. So then they say that the script A of R is bounded, which is proven previous page. And
Yeah,
then they say this next inequality, the convolution minus f of x is less than c times epsilon.
correct.
So how do we link that a sub 2k delta less than epsilon over and link to this inequality?
You go back to page 113,
Uh-huh.
right?
Yes.
And page 113, the first inequality says the integral is less than the integral absolute value of y less than delta
Mhm.
plus the sum integral of 2k delta less than y less than or equal to 2k plus 1 times delta,
Yes,
right?
yes. In the middle.
And
right.
the first one, this you get is less than or equal to some constant times a of delta.
Mhm. Yes.
And the second one you get is less than
C prime
well, the sum C prime times the sum 2 to the negative k a 2k plus 1 delta, right? And the a 2k plus 1 delta you basically get is less than epsilon C prime summation. I'm making a mess here. So this is less than or equal C times A of delta plus C prime summation 2 to the k negative k times epsilon over n, and summation 2 to the negative k
is 2.
Right. Okay, so this is less than or equal some constant, we call it k2 times epsilon, plus, since A of delta converges to 0 as delta goes to 0, this is less than or equal to epsilon for delta small enough.
Okay. I see. Okay. Thank you, Professor.
Okay.
That's it for me today.
In the book, when they use C prime, do they just mean a constant different from
just
C?
a different constant? I mean, you actually, if you look at analysis books, they use C as a constant and they use the same C for different constants all the time.
Okay.
Because sometimes you have all these inequalities listed and you don't have enough subscripts for them. So it is very common that they use the same letter for the same constant, meaning it's a generic constant.
Professor, the last part, in addition to this pointwise result,
yeah,
what is the identity they provide the conversions in the L1 norm? So because this is the definition of converge, because there are less than G1 numbers.
Yes. Well, in theorem 2.3, theorem 2.3, the big result is that f star k delta is integrable. That's the important one. And then if you look at a sequence delta n which goes to 0 and decide fn is equal to f star k delta, then fn converges to f pointwise, right? That's the result of theorem 2.1. That's what theorem 2.1 says. Pointwise almost everywhere, right? And
yes,
now you have a sequence f n star converging to n, and if fn converges pointwise to n, then fn minus f in the L1 norm converges to 0. So after you have this delta n here, after you have f times k delta convoluted with k delta is integrable, then you're, I guess you could use either the monotone convergence theorem or dominated convergence theorem. Your dominated convergence theorem will give you theorem 2.3, the convergence in theorem 2.3.
Thank you, Professor.
Yeah. Okay. Let's go to the problems. Exercises, I mean.
Yes. $145.
145. Okay. Exercise number 1. Suppose phi is integrable with and k delta is delta to the minus d times phi over x divided by delta, and we have to figure out that this and integral phi over rd equals 1. And we want to show that this is a family of good kernels. And so what do we have to show? We have to show the properties of good kernels, which is 1, 2, and 3.
On page 109.
Yeah. Property 1 is done, right?
Right.
Because that's here. Property 2 is done.
Because it's bounded.
Because it's integrable.
Integral.
Integrable means that its absolute value is integrable. And
I see.
the integrable phi of I mean, I haven't done it yet. I do that for 1, 2. You make a change of variables, and according to the change of variables formula, so you make x over d equal to u, then the du is equal to
DDU, yes.
dx over delta to the power of dx over delta.
That's for the
right.
d-dimensional, yes.
Yeah. So this is just phi of u du. And that gives you exercise 1 and 2. So property 3 is we look at the integral of absolute value x greater than or equal to eta absolute value k delta of x dx. This is the integral absolute value x greater than or equal to eta delta to the negative d phi of x over delta dx, and this is absolute value phi of this is less than or equal, or we said phi is not negative, I think. This is less than or equal to delta to the negative d times the L1 norm of phi and this goes to 0 as delta goes to 0. That's pretty straightforward. Now, part B. If in
Professor,
addition,
if the delta goes to 0, doesn't it go to since the delta is in the
oh yeah, right. Okay, I have to redo that. Okay, this is, we do change of variables again.
Okay.
If x is less than eta, then x over d is less than u is greater than eta over d, and here we have absolute value phi of u du. Everyone agrees with that?
Okay.
And again with proposition 112. Part 1.
Professor, the
Yeah.
the delta to the negative d power doesn't cancel?
It cancels, yeah.
No, you said du is equal to dx delta to the negative d power.
Yeah, it cancels.
It
If you look up here.
Okay.
And it cancels here too. But
oh yeah, that's right. I'm sorry. It cancels.
If x is less than or equal to eta, then x over delta is like x over delta is less than okay.
Yes.
Now given epsilon greater 0, there exists a delta small enough such that this ball where u is less than delta, well, this is not a ball, it's the complement of a ball. So by 112, if you make delta small enough, then the ball whose complement we are integrating over is large enough that this is less than epsilon, right?
That's right.
This is by prop 112 in chapter 2. Okay, so that does this. Now we have to show that it's the finite support thing, right? So I need another thing. So for part B, assume in addition that phi is bounded and supported on a bounded set, and so is contained in some ball of radius r around the origin, right? And verify that this is an approximation to the identity. So what we have to show is that k delta So this is the absolute value of delta to the minus d times phi of x over d, x over delta, and that's certainly less than or equal to delta to the negative d times the bound of phi, right? And so the first part so this is
Yes.
prime. And for the second one, we need to show that k delta of x is less than or equal, so which is delta to the negative d times phi of x over delta is less than or equal to a delta over absolute value x to the d plus 1. Okay, first, for all x such that absolute value x is greater than r, is r of this radius, absolute value x over d delta is greater than r, phi of x over delta times delta to the minus p is equal to 0, because, and this implies certainly this is less than or equal to a delta over absolute value x to the d plus 1, right?
Okay.
And now, so we only have to worry about x over delta less than or equal to r.
Professor, why that function is 0? Oh,
Because the support is contained in the
oh
ball.
yeah. I see. Of course.
That means x over delta is outside the support.
Yes,
If x over delta is less than or equal to r, then delta to the minus d phi of x over delta is less than or equal to delta to the negative d times m, and this implies 1 over delta is less than r over absolute value x, right? So 1 over delta to the power d is less than or equal to r to the d times m over absolute value x to the d, and which is equal to r to the power d m absolute value x to the d times delta over x. Delta over x is
bigger than 1 over r.
Bigger than 1 over r, but what is it less to than delta? Let's go back here. Let's do delta over delta, and 1 over delta is less than r over x. So this is less than or equal to r to the d plus 1 times m over absolute value x to the d plus 1. And I'm off the grid here, so it doesn't show up. Absolute value x to the d plus 1. Okay, so and
that's part 3 prime.
That's part 3 prime.
Yes. Thank you.
Okay, part C I'm gonna skip for the time being because we don't have all that much time. Problem 2 I will do next time as well. Because I want to do problem 3 because this is all the material. Okay. Suppose 0 is a point of Lebesgue density of a set E subset of R. Show that for each of the individual conditions below, there is an infinite sequence of points xn in East with xn not equal to 0, such that xn and xn goes to 0 as n goes to infinity. Okay, so and we said xn also contains binaries. So for part A, I'm gonna look at the set A, which is the set of all x in E, such that negative x is also in E. And all I have to do is I have to show that A is not finite. If A is finite, to show that, suppose A is finite. And then look at a sequence xn, which goes to 0. And look at the sets negative xn plus xn, which is negative xn comma 0 union 0 xn.
Yes.
Okay. So if the left set has positive measure, then only for finitely many points in the left set, there is a corresponding point in the right set, right? This has measure 0 if the set is finite. Because if both sets have positive measure, that would mean
infinitely.
That would mean that there's infinitely many points in both sets, and that means there's infinitely many points in the set A, right? But if A is finite, that can't happen. Similar, if the right set has positive measure, the left set has positive measure 0. That means the measure of the set negative xn intersected E has to be less than or equal to the absolute value of xn. because one of those things has 0 and the other one has measure less than absolute value n. And that means the measure of minus xn xn intersect E divided by the measure of the ball negative xn to xn has to be less than 1/2. Right? The top measure is less than or equal to 1/2. Right? And that means there is a subsequence of balls whose measure converges to 0, which is less than or equal to 1/2. And that means this thing cannot converge to 1, right? Which means that 0 is, because 0 is in each of these sets, 0 cannot possibly be a point of Lebesgue density. Right? So therefore, A is infinite. Okay. So pick any sequence in A. Right? Then if you have the sequence xn, the sequence of the negative xn is also in A, right? Both sequences are bounded sequences. And then you just pick a subsequence which is heading to 0. I mean, you could start with an x1 and negative x1, and then you restrict A by the additional restriction that the absolute value of x is less than x1, which still has the same property as all this. And then you can pick an x2, etc., and you get a sequence that converges to 0.
Yes.
B is exactly the same idea. You just make A is the set of all x in E such that 2x is in E as well. And with exactly the same argument, you can show that A has to be infinite. And then you can pick a sequence and a subsequence of that which converges to 0. But the key is this one. A is not finite. And the same as this, A is not finite, because if A were finite, you would get that contradiction.
Yes, sir.
Okay, and I'll do 2 next time. And let's see, what are we gonna read?
Oh.
We're gonna have to read something.
Yes, rectifiable.
I can recommend some crime novels if you want.
Differentiability of functions.
Yeah, that's a crime novel too.
Oh, bounded variation finally.
Bounded variation. Okay. Read page 114, differentiable of functions, but not the complete thing, up to 122 to the end of corollary 3.6.
Okay.
So you have the rising sun lemma in there.
Yes. It's a sunny place to stop. I see. Rising sun lemma.
Yeah.
That's the path that Professor Haydn finishes in one day.
And I'm not gonna assign any new exercises. We still have to do 2 and
Yes.
1C. Okay.
Yes, sir. Thank
Okay,
you, Professor.
and Julie, if you can send the MP4 file to either me or Angela,
Uh-huh.
and I or you, we can ask her to post it on
Her account.
If you possible, send for all of, because we needed this one too.
Oh, yeah. Angela is going to post it on the YouTube, I think. Then you can just watch it
yeah.
whenever.
Oh, you can send it to all of us. It's just
Sure.
it's.
I don't have an email address.
Yeah. Then you can send it to me, and I can send it to all of you guys.
Sure.
And there is a class list for this, which I don't know off the top of my head, but I use it all the time because I have it in my email integrated. So if you send it to me, I can send it to the rest of everyone.
Okay, I'll send it to you, Professor. Professor, before sign off, can I ask a quick question about that? The ratio of the measures less than 1/2.
Yeah. Why is that the case?
Yes.
Well, the measure of the interval from negative xn to plus xn is 2xn, right?
Okay.
And the measure of the interval negative xn to plus xn intersected e is less than or equal to the absolute value of xn, because one of those 2 intervals has to have measure 0 if a is finite, right? And so it's xn divided by 2xn, which is 1/2.
Fair enough.
Yep.
Okay.
Elementary.
Yeah, elementary. Very easy.
Yeah. So
Okay.
that's where it comes from.
Yes, sir.
Okay, I adjourn this meeting.
Thank you, Professor. Have a great evening.
You guys have a great evening too.